by mathematical induction that 2 to the 4n plus 31 to the n minus 2 is divisible by 15 for all positive integers n. We start by writing the proposition for this statement. We have 2 to the 4n plus 31 to the n minus 2 is divisible by 15 for all positive integers n. So we can write this for all positive integers n. Check that the first case is true. The first case occurs when n is 1. We need to check that the proposition is true when n is 1. We replace n with 1 and we have 2 to the 4 plus 31 to the 1 minus 2. So that is 16 plus 31 minus 2, which is 47 minus 2, which is 45. And this is divisible by 15. We say that P of 1 is true. When n is k, for any positive integer k, we assume that the proposition is true. So if P of k is true, then when n is k, we have 2 to the 4k plus 31 to the k minus 2. This is divisible by 15. For some positive integer k. We need to now check that when n is k plus 1, we need to check that the next case is also true. We replace n with k plus 1, and we have 2 to the 4, k plus 1 plus 31 to the k plus 1 minus 2. That will give us 2 to the 4k plus 4 plus 31 to the k plus 1 minus 2. Now, from the law of exponents, we know that x to the a plus b, this is x to the a, x to the b, or we can just write this as x to the b times x to the a. It matters not the order. Then we have 2 to the 4 and 2 to the 4k. Then for this second part here, we have 31 and 31 to the k minus 2. That is a 16, so that is 16 times 2 to the 4k plus 31 times 31 to the k minus 2. We need to show that this statement is divisible by 15. In order to do that, let's look at 16 here. 16 is 15 plus 1. So we have 15 plus 1 times 2 to the 4k. And 31 is 30 plus 1 times 31 to the k minus 2. And use the distributive property. We have 15 times 2 to the 4k plus 2 to the 4k plus 30 times 31 to the k plus 31 to the k minus 2. Okay, we can group these two together and the rest as another term. That will give us 15 times 2 to the 4k plus 30 times 31 to the k plus 2 to the 4k plus 31 to the k minus 2. These two are multiples of 15. You have 15 and 30 here. This is divisible by 15, clearly. And this is also divisible by 15 from our assumption that the proposition is true when n is k. Then we can see that after that, we say that P of k plus 1 is true. The proposition is true when n equals k, when P of k is true. Hence, we say that, hence from the principle of mathematical induction, from the principle of mathematical induction, we say that P of n is true for all positive integer n.